In this lecture, we are going to talk about nuclear power plant. Nuclear energy has many applications, and one of the major applications that we are focusing on is actually producing power. And when we say nuclear power, I mean that we are using nuclear energy, which usually comes in a form of a fission reaction to produce electric power. And the upcoming advanced reactors, which known as Generation 4, is to focus on producing affordable electricity or electric power and to supply this electricity into locations that's currently impossible to reach out. And that's the main idea behind Generation 4. Cheap electric power and more accessibility by different places, different communities to these kind of energy under safe condition and safe handling and operation and more and more. Please keep in mind, some of you doesn't have even any knowledge about nuclear energy. So that's a very classical introduction class here. What's nuclear power? What's nuclear power plant? What's the other power plant? And maybe why nuclear is now the favorable one, or why we are actually looking for nuclear energy to produce power over the others. We are not eliminating the others. We are integrating the others as well. So it's still reliable. We're still using it, but the concept of clean energy, it's becoming more clear, and cheap energy as well. And nuclear energy is one of these resources that can actually meet these two major criteria. If I move to the next slide, this is an example of power plant. Power plant, the classical one, it's basically required a very important component known as turbine. And this is the component that we are talking about. Turbine is a kind of a device that's responsible for converting thermal energy, mechanical energy into electricity. So to do that, in a classical steam power plant, we create a steam generator, or sometimes we call that actually the boiler, and we feed the boiler with water. Then we use fuel and air to generate thermal energy that are going to convert that water into steam. This steam is going to go into the turbine, and we convert that thermal energy into mechanical energy. Then we can convert that mechanical energy into electricity. And that's the main process in any power cycle. It's to convert thermal energy that's coming with the steam into electricity. Now the steam has completed its mission, so it has to go somewhere. And because we cannot actually waste that steam because it's chemically treated and it's clean water and so on, so without going into details, but we don't waste that steam. So what we're going to do, we're going to condense that steam in a component known as a condenser. Then we pump it back to the boiler or a steam generator to keep the cycle going all the time. And what you see in the other side here, or the other side here, are secondary components. For example, it's the cooling tower, or sometimes instead of having cooling tower, we have the running river that we pull out water to use it for the condenser. If you want to condense steam, you have to have a cold liquid inside the condenser. So we use a running river to pull out water. If there is no river around, we can build a power plant or the steam power cycle and use cooling tower to replace that source of auxiliary cooling water. Then there is a chimney because we are burning fuel, and most of the steam power cycles are running by fossil fuel. We talk about coal, natural gas, and these kind of things. So it's hydrocarbons. When you burn it out, you're going to get some exhaust out. So you find that stack is major component as well. So this is basically the steam power cycle. And we call it steam power cycle because it's mainly the water that come into steam and so on. And the source of the fuel is actually fossil fuel. So that's very classical power cycle. And we have a lot of this in the United States and worldwide, and it's still going. Old generation of steam power plant was using coal, but advanced ones are using natural gas. But again, they are depend on fossil fuel that's running out from the reserve is going down, so we're looking for other options. Now going for a gas power cycle. Again, it's a cycle, it's a device that can produce electric power, but in this case, instead of using steam, we are using gas. For those who are coming from mechanical engineering background, they know what we are talking about. It used to call the Brayton cycle. For those coming from non-nuclear or mechanical or engineering degree, very simple. Again, the major component is a turbine. And instead of supplying steam with some energy, we are supplying gas. Could be xenon, could be air, could be whatever it is. So it's a gas, go through a combustor, which is a second name of, or a replacing component for the boiler or the steam generator, right? In the boiler, steam generator will convert water into steam. In the combustor, we are heating up gas. So we supply cold gas, get heated by burning fuel inside. You got that thermal energy carried by that gas into the turbine. The turbine is coupled to a generator in here. We got the electricity here. Then maybe the gas, if the gas is air, we can actually blow it out to the atmosphere. If it is expensive gas like xenon or something like that, we can actually take it back here. And if you recall, in the steam cycle, we used to have a pump here to pump liquid back to the boiler. For gases, we don't use pumps, we use compressors. So that's why we have a compressor here. And the compressor would take whatever is coming out of the turbine and push it back to the combustor. If you keep the cycle open like this, there is no connection between the turbine and the compressor. That's called the open gas cycle. If you add a second component here or connect the two components here, that's called the closed cycle. But sadly, the exhaust coming out of the turbine is really super hot. So we have to cool it down. Very typical to what we did in the cycle here. So whatever is coming out of the turbine, we have to cool it down to condense it so it can go through the pump. We do the same here. We take the exhaust of the turbine and cool it down with a second recuperator, or we call that heat exchanger. Then we'll put it back to the compressor and the cycle continue. One of the very famous examples of the gas power cycle is the airplane engine. Airplane engine is simply a gas power cycle in a simple language here. So again, that's a second type, or that's another example for a cycle that used thermal energy. In this case, we are using gas as an operating fluid to convert it into electricity. So that's another example here. Going for another example here for a power cycle, it's called the combined power cycle. As the population actually goes up, the electricity demand is going more and more, and now everything is coming into electricity dependent application. Look to your house. Even cars now are electrically driven cars. So the demand for electricity was going high and high. So we came with an idea is to create what we call the combined power cycle. Combined, it's coming from actually a combination between the steam power cycle and the gas power cycle. So if you look to the major component here, this is the steam turbine coupled to the generator to produce electricity. Then we have the condenser, the cooling tower, or a river, depending on where the power cycle is built. But in the same time, we have the gas turbine, compressor, exhaust gas, and here's a generator. So now the upper portion of that cycle is simply the gas cycle, and the lower portion of that cycle is actually the steam cycle. And they are connected by that heat recovery or recuperator I talked about that's supposed to be after the gas cycle. If you go back to here, I said if we want to close the cycle, we have to have a recuperator or a heat exchanger. Sometimes we call that energy recovery device. So that's the energy recovery device where we recover the energy from the exhaust gases coming out of the turbine and use it to heat up the water or the steam. So there is no, if you go back, that boiler or steam generator is no longer exist here. This is actually the steam generator. This is the boiler here, okay? And we are using, instead of burning additional fuel into that cycle, we minimize the fuel burning, and we use the exhaust gas carry the energy to steam the liquid or the water that goes to the turbine and so on. So that's what we call the combined power cycle. So now you add whatever that electricity generated by the gas cycle plus what's generated by the steam cycle to get more energy production. And we also minimized the quantity of fuel that we are burning. So we are getting more outcome for less income, which means that we are having a higher efficiency of producing electricity. The more or the higher the efficiency of producing electricity, the cheaper the electricity you are getting to the customers. That's one parameter here. That's the affordability of electricity. So that improved a lot the thermal efficiency. When we improve the thermal efficiency, we produce more electricity, bear the same amount of initial cost or the running cost that we are using for that power plant, which means that we can reduce the price of electricity. Another example of power cycle or power plant or power or electricity producing plant is hydropower. Hydropower is very simple. Again, the main component of any power cycle is the turbine. Here is the turbine. Then turbine in a simple language is a shaft, and there is vents or fans that's attached to it. We need to drive these vents or fans, whatever it's called, to rotate that shaft that's connected to a generator. You see, these are the turbine vanes here. Then you need to drive these vanes so the shaft will rotate. When the shaft rotates inside the generator, it will produce electricity. So the way we are driving this in the steam power cycle by high energetic steam coming out of the steam generator. In the gas power cycle, we drive that shaft by the high energetic gas coming from the combustor. Now, we can drive that shaft by the potential energy. So if we have a dam or water storage here, then we can build up water in the back, which means that we are storing potential energy. Then suddenly we can open that gate, allowing for that potential energy to go through a channel. That potential energy will actually drive that shaft, which will drive the generator and produce electricity. Then the water will leak out to the other side of the river. That's the idea of the hydropower. We are using, instead of using thermal energy that's contained in steam or gas, we are using the potential energy of the liquid that's stored behind that dam. Maybe this is down a river. We can actually, after we release that water, we can close the gate again, build up more potential energy, and the story continue. Or maybe it's one running river, but that river has different altitudes, so we can drive that potential energy difference into electricity. In some application, we can actually pump back that river water to behind the dam, store it in a high altitude or high level. Then we can convert that potential energy again into electricity. Again, that's another example of power. You realize for the last three examples, turbine is essential component. It's just the way how you drive that turbine. That's a key. And the rest of the components are secondary or auxiliary component that help you to keep the cycle going without wasting the resources that you have. Another example here is called the ocean wave power cycle. So we realize that in the ocean, especially at lower altitudes, deeply inside the water, there is waves. There are waves actually right there, and these waves carry a lot of energy. So one came with an idea: if we have balloons and links, and the waves is going to actually pushing these links back and forth, we can actually use them as pumps that's going to push water all the way to a higher altitude or higher elevation. And then we can drop that water over turbine blades, right? And that turbine blades will rotate the shaft and the shaft is coupled to a generator, and that generator will produce electricity. So we are using the energy stored in these waves to pump water to a higher altitude. You see that they are located 20 to 50 meters beneath the surface of the ocean. And because of these links, cross-linking are going back and forth, so they are acting as a pump. They are actually pressurizing the water that can go into very high level. Then you can drop it over the turbine to rotate that. Then you can push back the liquid into the ocean, back to the ocean, and the cycle continue. Again, major component is turbine. In this case, we are using the pressure energy or the wave energy stored inside the ocean depth to convert that into wave energy into electricity. Again, that's another example of power cycle. Another example of power cycle is the geothermal power cycle. And for those who doesn't know, that state of Idaho is one of the big geothermal energy storage. Geothermal means that we are having a lot of energy stored between the rocks and between the soil layers beneath Earth surface, which means that if we dig deeply inside Earth under the surface, we can actually extract a lot of energy from this. And Yellowstone is a big witness for that. But we have more and more. Pocatello has more. Around Pocatello, we have a lot of geothermal wells that contains a lot of energy. Last year, we had a simple project trying to develop a net zero power cycle or net zero plan for the city of Pocatello. So we used geothermal energy around Pocatello to be able to produce electricity so we can minimize the dependency on the fossil fuel power plant. So again, in a simple language, we dig deeply inside the underneath the Earth surface, and we can extract energy. If you pump cold water inside that layer, it's going to absorb energy from rocks, soil layers, and so on. Then that will be converted into steam. Steam will goes up into the turbine. Turbine blades will rotate, coupled to a generator. We got electricity. We push that cold liquid back. It's going to be heated underneath the surface, coming back as a steam and so on. Now, in some locations, houses can use that what we call geothermal heat pump, a device that can actually heat your house in the winter using the same concept here. So they are digging behind in the backyard, pushing a piece of pipe or tubing inside. They don't have to use water to be steam. Maybe the source of energy is not enough to convert water in steam. But there's some other mineral oils. There is some idea actually of using sewage water treated instead of wasting it to use it for generating this kind of energy here. But you can dig a pipe in your backyard, extract the energy from ground, and use that energy to heat up your house. That's called geothermal heat pump. And the concept is becoming more popular right now. If you Google that, you will find there is multiple companies can actually produce that device for you and make it very efficient. Let's move to another example. Wind power cycle. And I think Idaho also is very famous with wind turbines. You see that in Idaho Falls, you see that in Pocatello, you see that in Boise, you see that around Salt Lake City border. So in a simple language, we are converting the wind energy into electricity. Again, we have a huge blade turbine, usually 3 or 5 blades. I don't know the idea why it's an odd number, but usually there are 3 or 5. Then the wind comes in, it's going to rotate that blade. The blades is connected to a shaft. The shaft is coupled to a generator. Generator will produce electricity. You can take it directly to the grid, or you can store that energy into a battery system, and you can take these batteries to locations where it's needed. Again, in this case, we are converting kinetic energy in the wind into electricity. That's a concept of a power cycle, is to convert one energy into mechanical that leads to electricity because of the generator component. Again, all of these are actually, they come under renewable energy, power plant, wind, geothermal, ocean, hydro. These are all classified under renewable energy, right? Moving forward, another type of power cycle is the solar power cycle. In this case, we are converting the solar energy, the heat that's coming from the sun, into electricity. But we do that by multiple ways. But the most famous one is to use solar panel. Maybe you have photovoltaic cells, whatever they called in the ECE department. But it's capable of converting the thermal energy from the sun into electricity that can go to the grid, or can be stored in batteries, or can be actually used directly, whatever the application is. But again, we know that it's another form of clean energy, renewable energy. I'm not discussing the concept of the cost of each one of them, the efficiency of each one of them. I'm just exploring different ideas behind these power plants to convert that into electricity. But for example, people know that solar panels have a very low efficiency. So their efficiency is very low. That's why you need large surface area of solar panel. You see the solar field is huge, right? And you look to the outcome out of this solar field, it's nothing. It's because the efficiency is very low. So these are all a secondary type of power cycle that could help next to a major one. So for example, if we have a power cycle, steam or gas or combined, that's feed the city of Idaho Falls or the city of Pocatello. Maybe when we are under the peak demand of electricity, there is a circumstances that we need excess energy. Could be the wind, the solar, the ocean, whatever these kind of renewable energy can feed a little bit of extra, right? But we still relies on the major power cycle, steam, gas, combined, and the most one should be the nuclear. But again, we are exploring ideas here. Going further, now we come to the nuclear power cycle. And let me spend a little bit more time here to explain the difference between the nuclear power cycle and the other cycles we have seen. Again, if you look to the component of the nuclear power cycle, you will find there is a turbine here. Again, there is no turbine, no power. So turbine is a major component here that need to be rotating and coupled to a generator to get the electricity. And this is happening by steam. Steam is coming from a steam generator. So that blue cycle here is simply a steam cycle. This is simply a steam cycle. Except we don't have a boiler or a steam generator to burn fossil fuel into it. So what we're going to do, we're going to have a secondary loop that's colored red here. That's a nuclear reactor where the nuclear fuel is sitting inside here. We have a nuclear fission reaction that produces electricity. It's produce thermal energy. Thermal energy will be circulated, hot liquid is going to be circulated into the steam generator to produce steam. That steam will continue to drive the turbine, condense back in the condenser. That feed water, maybe it's coming from a running river or it's coming from a cooling tower. Then it's pumped back to the steam generator. But we're using the thermal energy coming from the fission reaction from that reactor vessel to convert the water into steam. So this red cycle here, the primary loop, that's how we call them. It's replacing the boiler or the steam generator or the combustor in the gas cycle. So instead of using fossil fuel to burn it to get thermal energy to convert water into steam, we are getting the fission reaction thermal energy produced, and we use that into creating steam and putting the cycle into operation. That's nuclear power cycle. So the only difference between the nuclear power cycle and the classical cycles is the source of the thermal energy. It's coming from nuclear fission. Now we need to look to how people actually classifying nuclear power plant or classifying the nuclear reactor. There is no standard way you can classify the nuclear reactor. Again, I'm talking to people who doesn't know the terminology, the terms, the definitions. So, for example, one of the way we can classify nuclear reactors is look to how the fission reaction occurs. Fission reaction, as we're gonna actually explore later on in the course, it's an interaction between what we call newborn neutrons and nuclear fuel. So as soon as a neutron hit nuclei or nucleus of a nuclear fuel, like uranium fuel, uranium-235 fuel, it's gonna cause fission to that nucleus. It's gonna break down, and it's gonna produce more neutrons, and it's gonna produce thermal energy. So it depends on the energy of that hitting neutron to that nucleus. If the neutron is coming very fast, we call that actually fast neutron reactor. If it's coming slowly, we call that thermal neutron reactors. So we can classify the nuclear reactor based on the level of kinetic energy of the neutron. And how we control that? We control that by something called moderator. That's going to talk about in a few seconds, or the next one. But the moderator is what's responsible for keeping the energy of that neutron alive, or it can actually slow it down so it becomes thermal. So we can control that. The second way we can classify nuclear reactor is based on that moderator. As I mentioned, moderator, one of its function is to slow down neutrons so they can lose kinetic energy, they become slower, and we can classify the reactor as thermal neutron reactor. We sometimes use water as a moderator. We sometimes use graphite, depending on the type of the reactor, and we're going to talk more in details about this. Another way you can classify the nuclear reactor is looking into the shape of the fuel, nuclear fuel. Some reactors are designed to use cylindrical shape of fuel. We call that rods or pins. Some reactors are designed to operate with a nuclear fuel that looks like flat plate. So we call that flat plate or plate type fuel. So that's going to be a plate type reactor, fuel reactor. Some are designed to operate using a nuclear fuel in a shape of a sphere, spherical type fuel. In a different language, we call that pebble bed reactor. Or some reactors are designed actually not to deal with any solid shape of a fuel. Cylindrical, plate, spherical, these are solid shape of the fuel. But some reactors are actually using molten fuel in a form of a liquid. That's another type of reactor. So we can classify the reactors based on the shape of the nuclear fuel. What I'm listing here are just examples. You may find other more bases to classify the nuclear reactors, but I'm talking about the most commonly used terminology here. The last one in the list I have here is actually to classify the nuclear reactor based on the coolant. If that, again, as we mentioned here, this is the primary loop, this is the secondary loop, right? So there is a coolant here that need to absorb energy from the primary loop to convert liquid, which is the big chunk of blue lines here, into steam. So this is actually a secondary coolant here. And there is a primary coolant here, right? So there is primary coolant, there is secondary coolant. The primary coolant is very important because this is what cool down the reactor core or the reactor vessel. If we don't cool down the reactor vessel, we're going to go overheating and we're going to lose the reactor. So the primary coolant is very important. Secondary coolant is also very reliable on the power cycle here. Again, we're going to talk about different types later on. But looking to the coolant, some of these reactors are using water. That's what we call the light water reactors, right? That's one of them. Some are using molten salt. So we call them molten salt cooled reactors. Could be fluoride salt, could be chloride salt, different types. There are designs that using liquid metals, sodium, lead, lead bismuth, and so on. So we call them actually liquid metal cooled reactors. And some of these reactors are designed to be cooled by gases like helium, and we call that gas cooled reactor. So now when you hear light water reactor, molten salt cooled reactors, liquid metal cooled reactors, gas cooled reactors, you understand that the primary coolant inside the reactor core is water, molten salt, liquid metal, or gas. As I mentioned, this is just very simple basis or the most commonly used one, but you may find others to classify the reactors. So, for example, this is the same nuclear power plant that we explained a few minutes ago. And this is classified as light water reactor. Why we are classifying it as light water reactor? Because the primary coolant is actually water. Actually, here the primary and secondary loop contains water. And light water reactors, we have two major types of light water reactors. For those doesn't know, we have something called pressurized water reactor, and the second type is called boiling water reactor. And it's obvious from the name, the boiling water reactor, we allow liquid to boil in the primary loop. So we don't have that connection here. We actually take cold liquid here, goes into the reactor vessel, boils, we take the steam up here. So we don't have that connection here. That's in the boiling water reactor. In the pressurized water reactor, we cannot allow water to boil inside the reactor core for many reasons, and we're gonna touch base with that later on in the course. But we use a component called pressurizer. That's to increase the pressure of the primary loop, so it doesn't actually allow water to boil in that primary loop. It's allowed to boil and convert it into steam in the secondary loop. That's fine, because we need that steam. But in the primary loop, if we are using pressurizer, that's indicating this is the pressurized water reactor, which is one of the light water reactors type. So it's clear that diagram here is presenting the pressurized water reactor. That's why I put the question mark here to explain how to get it. It's because of that pressurizer. And you realize that we always like to have all the nuclear exposed material enclosed in a big house called the containment structure. That's a big concrete house. That's a big concrete house that contains the potentially radioactive material to be contained inside that loop here. And again, that's a light water reactor, pressurized water reactor type. This is the boiling water reactor. It's still a light water reactor type, but in this case, you see that the cold fluid is coming directly into the reactor vessel, exposed or in touch with the nuclear fuel, converted into steam inside the reactor vessel itself. Then the steam goes to the cycle. Again, if you have a pipe break here, you are exposing the outside community to radioactive material. It's true also in here, but chances to contain radioactive material inside is much higher for the pressurized water reactor compared to the boiling water reactor. But the main difference is there is no pressurizer, so we are allowing for the water to boil into steam inside the reactor core itself. So these are the two types of water-cooled reactors called light water reactor, pressurized water reactor, and boiling water reactor. We talked about classifying some of these reactors based on the coolant, right? So this is, these are like different schematics you can see for generation for liquid metal cooled reactors. You see that this is the reactor core, where the nuclear fuel is, and the primary coolant here is sodium, right? And there is a heat exchanger here to exchange energy between the primary coolant and the secondary coolant that's circulated inside this loop here. And in many cases, we are using also another sodium into that loop, depending on the application. But you could have sodium and sodium here, or could you have sodium and less reactive liquids to protect the reactor core itself. But I see there is a heat exchanger here, the heat exchanger here. Then again, this is a secondary loop. So in this case here, you can see that we have the primary loop, but we have intermediate loop that's enclosed in that dashed line. This is called the intermediate loop. Then you have the secondary loop to convert energy into electricity. Again, the same component. It's a turbine, a condenser, a generator, and so on. Another layout or design. Again, this is the core. Liquid metal is circulated here. A couple of heat exchanger that exchange energy with a secondary loop. So there is no intermediate loop here. This is a secondary loop. I could have a secondary loop on the left side as well, but that buffering intermediate loop is not exist in that layout. Again, it's different conceptual designs that exist in the market people talking about. And by the way, this is actually a very classical standard layout of liquid metal cooled reactors. Moving forward, gas cooled reactors. Again, this is a reactor core. Now, instead of using liquid metal, we're using helium, and the helium is circulated inside and pulling out energy going directly to a secondary loop. Whereas you see multiple turbines, you can get, you break down the gas here, you got energy, you got electricity, and then you push it back, secondary turbine, or this actually the compressor. So this is gas cycle here, okay? Because we are using helium, so it's better to use gas cycle. You may couple that gas to a heat exchanger that's connected to a water tank, so you can create steam. Then instead of using gas cycle, you can use steam cycle. But why we have to go into multiple stage if we can use the gas directly into the gas cycle? So it's always preferred to couple gas-cooled reactors to gas power cycle. Just zoom in on the reactor core. You're gonna see that this is one of the designs here. And you see that this is a nuclear fuel. It's a kind of like spherical shape. That's why we call that the pebble bed reactor. You see, they are actually spheres. This sphere is about 6 centimeters in diameter, and it's made of ceramics material, and it's included inside what we call the kernel or the fuel particles itself, trisol fuel particles inside. So, but again, we are talking in general here about the layout of the gas-cooled reactors. Molten salt cooled reactors, you will find many conceptual design right there. Again, the concept is the same. This is the reactor core. We should be circulating molten salt. Could be one of the very famous fluoride salts, FLiBe, fluoride, lithium, beryllium mixture. There is chloride salts as well. So you circulate that salt, and again, you have intermediate loop. Then you have the secondary loop. And again, you are free to choose between gas cycle or steam cycle, because it depends on what liquid you have in the intermediate loop, right? You could have molten salt in here, then you could have water in here, actually, or secondary salt, and you can have water and replace this with steam cycle. Or you can have actually circulated gas and use gas cycle. So this is specifically gas cycle. There is a generator, a turbine, there is a compressor here, so that's definitely a gas cycle. This is a layout of a second example of a molten salt cooled reactor, and this is KPFHR. This is very famous. This is Kairos Power fluoride salt high temperature cooled reactor. I was honored to have that concept actually built back in 2014, 2015 at University of New Mexico, where I actually was doing my research. I was part of the team working on that conceptual design. Now it's reality. Kairos Power is one of the most progressing company in actually manufacturing a prototype. They are doing that in Tennessee. They are building permit prototype. It's a 1-to-1 scale reactor, but it's not using nuclear fuel yet. It's electrically heated for demonstration purposes and testing. then it's going to be the last stage is actually fueling the reactor and move forward. So I believe that Kairos Power is going to be one of the existing reactors designed, not in a blueprint, but it will be in reality. Again, we are just exploring different types of conceptual design for Generation 4 or Gen 4 reactors. Let's take a little bit focus here. You remember we talked about the big concrete housing for the nuclear fuel. That's called the building containment. As I mentioned, it's a thick concrete. So if there anything that happened for the nuclear fuel inside the reactor, everything's supposed to be contained in this house. Then we have the reactor vessel. This is where the nuclear fuel is. So now I'm focusing on the nuclear part, okay, of the power cycle. Nuclear vessel or reactor vessel, where the nuclear fuel is here. Lower plenum, upper plenum. These are the bottom and the head of that reactor vessel. Primary loop. And there's a pump. There is a pressurizer. So we are focused here about the pressurized water reactor. Then this is a steam generator where the energy coming from the fission reaction is going to be exchanged, and that steam generator, which is simply a heat exchanger, to convert liquid into steam. So this is a picture of the real system here. So this is the reactor vessel, which we simplified by this. Upper header, lower plenum, and the fuel is stacked inside. What you see up here, these are called the control rods, which is here. These control rods are responsible for actually shutting down or reducing the power, shutting down the reactor, reducing the power, controlling the power level, and so on. That's one of the functions of the control rods, or starting the reactor. Then you can see that this reactor vessel is connected to 4 different steam generators. This is 1, 2, 3, 4. So 4 steam generators. And there's a pump here. So each steam generator is attached to a pump. 1, 2, 3. The fourth one is in the back, it's not shown here. So the reactor, a pump, the reactor vessel, which is this, a pump is here, steam generator, and there is one pressurizer that's serving the 4 loop. So this is called 4 steam generator loops. And you will see that the hot fluid comes from the top. So there is a hot fluid coming out. We call that hot leg, right? Goes to the steam generator, then it goes back to the pump, then the cold leg going back. So the fluid coming out hot from the reactor vessel to the steam generator and producing steam, goes out from the top, then it's pushed back by the pump to the cold leg and going back to the reactor. We talked about control rods. Control rods could be made of bronze, cadmium, silver. These are material has the ability to absorb neutrons. So if I want to shut down the reactor, you kill. We said that at the beginning there is a fission reaction. Fission reaction means that there is nuclear fuel. You hit that nuclear fuel with neutrons. It's gonna split, create energy, and produce more neutrons. If you leave these neutrons keep burning, keep actually born inside the reactor vessel, the chain reaction will be continuous and it's overheating. It's a problem. So have to control that level of reactivity inside the reactor. So these control rods are made of material that they can absorb neutrons. So if I want to shut down the whole reactor, I put all these control rods down all the way. It will absorb all neutrons, so it's going to kill the reaction. Usually the reactor vessel is made of authentics, stainless steel alloys, different layers. Most of the components now for the advanced reactors are made of different stainless steel alloys, even for molten salts and liquid metal cooled reactors. Let's focus more deeply into this guy, the reactor vessel, how it looks like. This is the reactor vessel. These are the fuel rods inside, control rods at the top, and the inlets and the outlets of the reactor vessel. So we stack the nuclear fuel inside in something called the fuel assembly. And this is a schematic showing what we mean by fuel assembly. They are groups of arrays of nuclear fuel. So this could be 15 by 15 assembly could be 20 by 20, 25 by 25. It depends on the level of the power. So that's a single fuel assembly. And these are the fuel assemblies. And these are stacked inside here. And the coolant is going through them to carry out the generated energy. So the fluid is coming usually from the bottom, absorb the energy coming from the fission reaction, and leave from the top. So that's the layout here. If I take one or a single fuel assembly and I want to see how they are, it looks like a square here, right? The fuel rods are stacked in square shape, which is the lower part here. We call that actually the square array. So one of the way you can stack the 15 by 15, 20 by 20 fuel rods is to stack them vertically in a square array or square lattice. And the easiest way to look into that is to pick 4 of them and see what pattern is actually repeatable here. And that's clearly it's repeatable square pattern. So we call that actually square lattice fuel assembly. The other way we can actually arrange that 15 by 15 or 20 by 20 is to stack them in that shape here, whatever that hexagonal shape. But if you look into that and you pick up the repeatable pattern here, you will find that there is triangle pattern that's actually repeatable all the time. We call that actually triangle array or triangle lattice. So most of the fuel assemblies are arranged in square lattice or triangle lattice. That's a major configuration. And either in here or here, this is how we arrange the fuel. And between the fuel rods, it's just the fluid is flowing from the bottom to the top, right? To cool down these fuel rods. Here, that's a channel. That's why we call that subchannels. And when we look to the arrangement of the fuel assembly, D capital is the diameter of the fuel rod. And we're going to talk about that fuel rod in the upcoming 2 slides in details. What's inside it? This is not the fuel itself. That's a containment, a protective layer that contains the fuel inside. But we're looking for the outside diameter here. That's called the diameter of the pin or the fuel rod, D. Then the spacing here is called the pitch between the fuel rods. Could be here the pitch. Remember, this is a square lattice. So this is pitch. Horizontally, it's still P. The same for that's equilateral triangle. So that's P. That's P as well, right? So these are the major assemblies. So now let's pick one of these fuel rods and look what's the construction of it, how it looks like. So again, that's a single fuel assembly. It has 25 by 25, 20 by 20, 15 by 15, doesn't matter. Then I picked one fuel rod, and that's how it looks like from inside. The fuel rod is simply the nuclear fuel pellets, small cylinders, maybe a few millimeter in diameter, 9 millimeter, 8 millimeters in diameter, and maybe one less than an inch in height. You stack all of them together. Then you put all of them in a cover, in a container. That container called the cladding. So that's a picture here showing the nuclear fuel. And this is for a scaling purpose. So you can get the sensation how small or big they are. Then we take a bunch of them and we stack them over each other. Okay. Then at the top, we put a spring so they don't actually get misaligned. So that spring is going to push down over these fuel pellet to be sure that they are aligned all the time. There's no way for one of them is like, get out of the row and get in touch with the cladding. And the cladding is the big container outside. This is the cladding. And between the fuel pellets and the cladding, you realize that there is a gap. So the fuel pellets are not touching the cladding. That's a kind of an accident scenario that we don't like to have it. It's called fuel cladding mechanical interaction. That's could lead to a flare, but we leave a gap between the fuel pellets and the cladding. So see, that's a cladding, fuel pellet, and there is a gap. And this gap in the old designs in the light water reactors is filled with helium to just be sure that we are, keeping that separation. In some of the advanced reactor design, we are actually filling that with sodium, something that's highly conductive, so we can actually conduct energy quickly from the fuel pellet to the cladding to the coolant. Keep in mind, the coolant is touching the cladding from outside. So there is a coolant here. You can see there is a water flow here between multiple fuel rods. So we would like to conduct the energy quickly from the fuel pellet through the gap to the cladding to the coolant. Okay? So this is how it looks like. There is more advanced talks about fission gas. That fuel is going to produce bad gases. It's going to be released. It's going to get out through that gap. It's going to be accumulated at the upper cap or the upper head of the fuel rods. Again, that's early to talk about this right now. But again, this is multiple rods, right? As part of that fuel assembly, fuel pellets, spring is loading over them. This is called the upper plenum. And again, the reason of the upper plenum is to collect the fission gases. We filled that originally with helium for light water reactors or other liquids such as sodium for advanced reactors. Then the coolant is going into the sub-channels between them. Okay? So this is just more highlight on a single fuel rod construction, how it looks like. Again, as we mentioned, there are different types of nuclear fuel shapes, right? We talked about cylindrical fuel shape, which is simply, this is the cylindrical fuel shape here. That's a classical one, standard one. And there is spherical fuel shape. And this is what we call the fuel sphere here. And this is, I don't want to say it's designed specifically for gas-cooled reactor. For example, FHR, Kairos Power Reactor, is using actually spherical fuel spheres into the reactor core. So this is how the core looks like. These are the spheres, and the coolant is coming from the bottom to cool down the reactor and goes up. And that blue line is showing that this is not a stationary reactor, so we are pulling these spheres and put it back into there for a reason. So what's the construction of that 60 millimeter diameter sphere? As I mentioned, it's mainly made of ceramics material. You see that there is graphite layer with 5 millimeter thickness here. Then inside, these are the fuel particles. So it's coated particles. We call them TRISO fuel particles. TRISO fuel particles embedded into graphite matrix. So if I zoom in into one of these TRISO fuel particles, this is a layer of the TRISO fuel particles as well. It's multiple ceramics layer, and this is the kernel. This is the uranium fuel. This is where the fission reaction happening. And the reason of these all multiple layers is to keep the integrity of that fuel particles and keep the fission gases trapped inside. Fission gases is a big concern, especially at near the end of the lifetime of the fuel. We may or may not talk about this, but we like to keep the fission gases trapped inside the fuel. Chances are less with this kind of fuel shape, so they get released easily and build up a pressure inside that gapping. It could actually lead to high pressure. They could lead to a failure, and if they get out the fission gases, it's an accident. We don't like to see that. So with advanced shapes of fuel, like the spherical fuel here, we are trying to minimize the chance of fission gas to be released out. So they created that TRISO fuel particles, where the fission gases will be generated from the kernel, but it will experience multiple layers of ceramics. Ceramics mean that there is no porosity, right? They are highly dense material. They are strong, thermally conductive, so they can actually push the energy out, but they will keep the fission gases in. This particle here is about 1 millimeter in diameter. You have thousands of them stacked in that graphite matrix to form that 60 millimeter diameter sphere. You can see this is the TRISO fuel particles, just to get the sensation of the size. There are maybe thousands of them next to the pencil tip, right? Because they are very, very minor. For those who actually get the chance to visit the site or the MFC facility, they have a couple of them actually in a glass bottle. They can show it to you. I'm sure some of you maybe get the chance to see how they look like. But this is, again, more focusing on a different type of a fuel. In some designs, instead of stacking these TRISO fuel particles in a spherical shape, we can stack that TRISO fuel particles into cylindrical container as well. So instead of having that solid cylinder, that's pure uranium oxide, maybe fuel pellet, that's a solid material. No, we can have a container that contains trisulfide particles. So we minimize the chance of fission gas release as well. So just a different design. One of the most interesting designs I have seen was the TCR reactor core, transformal challenging reactor that's came a few years ago by Oak Ridge National Lab. It was a conceptual reactor design. You see, instead of having that cylindrical shape filled with the trisulfide particles, they invented that shape and filled with trisulfide particles. Then they stack maybe 6 of this. That's a fuel pellet now. They stack like 6 of them into a big container, and that's a fuel rod. The TCR was the first concept to use additive manufacturing, 3D printed core. So that's 3D printed container for the fuel element itself. Again, that was a concept that came a few years ago. I think it's fully died out. No one is talking about it right now. But again, this is just to give you an example how people are thinking about changing the shape of the fuel pellet itself and how to use the trisulfide particles into a different configuration here. I think that should conclude that introduction about what's nuclear power, different types of power cycles or power plant. Nuclear power plant, different conceptual one. What's fuel assembly? What's fuel rod? What's fuel particles? It's meant more for providing some of the terminology that we are using. Again, keep in mind, we are talking to some of you who doesn't have any background in nuclear engineering. So I would like to be sure that we are in the same page, same terminology here. I don't use acronyms too much. Again, it's quite of a challenge, but especially in nuclear engineering, some of you know that. But I would like to at least get the basic terms that we're going to use along that course or along the upcoming recording, so you guys can follow up what we mean by fuel rod, fuel pellet, gas gap, fuel assembly, right? Reactor vessel, reactor core, control rods, building containment, and so on. So moderator, what does that mean? Primary loop, secondary loop. I would guess these are the outtakes from today's lecture. We introduce a lot of terminology here, and you need to be aware of them as we go. So that's conclude that portion of the nuclear power introduction.